I came in and I thought for sure I was late, but there's no one else here. Okie dokie. Final exam schedule is posted. That's important. Our final exam is the not so fun 6 to 9 slot at night, but it is early in the exam schedule, so I guess that's nice. So our final exam is December 12th from 6 to 9, and it is in C368, pretty sure. They do have a note that it's subject to change, but between me and the recording, our exam hasn't changed in all the drafts that have come through, so I feel like it's gonna stay pretty stable. And besides, even if you do book your tickets off of this and it does change, then we have to accommodate that because they made a mistake, which has only happened once, but it has happened. All right, so we were working on a problem last day. Let's see here, let me grab that. In fact, how can I snag this whole copy? This whole bit. Paste. Okay. We did say finish on Thursday, which is today. Yeah. So as far as we got, right, we looked at what's the population and what's the sample proportion. And then we were asked to find the name of the statistic that we can use to measure the uncertainty of the point estimate. And remembering from last day, that is the standard error. Standard error of p hat. Just as a reminder, right, the standard error behaves the same way as the standard deviation, except we needed new terminology because it's talking about a point estimate instead of one observation. Okay. So standard error is just a special term for the standard deviation of a point estimate. Okay, but it behaves the same way and we'll use it in the same way. Okay, so then we were going to find the standard error from part D. So we said that the standard error, and this is from last day, but I'll just remind you that the standard error of p hat is technically the square root of PQ over N. But then one of the problems that we had was that we don't know P because that's the population proportion. So we replaced it with our next best thing. So then we're going to use P hat Q hat. So I wonder if there's something going on campus, or are you guys just slammed? Yeah. Sometimes there's more fun things going on than class, which I get. All right. So our standard error is going to be, I'm going to use 0.127, just rounding this a little bit. So I'll use 0.127 times 1 minus 0.127. Divided by N, which we said last day was the 212, right? So we're talking about defective chips in computer chips being produced. for a specific week. And so we found the sample proportion of defective chips was 0.127 and divided by n, which is 212, which gets me to approximately 0.022867, which I'm going to round to 0.0229. Just to kind of keep it more concise. I know, how weird of me to do 4 decimal places and 3 decimal places. I know the biology part of this course is cringing, but it's okay. Okay, so now we've got this spread for the sample proportion, because what we talked about last day was, okay, well, I've got one sample proportion, right? And so, but if I went out and I collected a new sample, right, I would find a slightly different sample proportion, right? So that's how we got that distribution of sample proportions. So now we have the spread of the sample proportions, essentially. Part F asks says the historical rate of defects is 10%. Should the engineer be surprised by the observed rate of defects during the current week? So what did we see? We saw 12.7% as the rate of defects, right? So is 10% that different, or is 12.7% that different from 10%? How can we quantify that? If we have the spread, right, we can standardize this to see how many standard errors 12.7 is from 10. Right? So that's going to be one of our kind of key tools for figuring out how extreme values are. So part F, let me just grab this here, because I do want to rewrite it in terms of how the two compare. Okay, so really what this is saying or asking is 12.7% extreme compared to 10%. Okay. How we measure if something is extreme is through a standardized score. Okay, so we can standardize. We can standardize 0.127, okay, to see how many standard errors it is from 0.1. How many standard errors it is from 0.1. So to standardize is really calculating a Z-score. And I want to know how far is 0.127 from 0.10 if the spread is 0.0229. If I do this, I get a Z of roughly 1.179. What does this mean? It means that 0.127, which we saw, is 1.179 standard errors away from 0.1. Right? In terms of classifying something as extreme or not, we use a guideline of more than 2 standard errors away is going to be considered extreme, right? So this is still within 2 standard errors. And so we say, that's fine, that's within the expected range. Okay. Let's make a little side note here. Note, and maybe I'll put it down. Boy, made it huge, that's okay. Just roll with it. Note. That makes it sound, well, it is important actually. So sure. Makes it look a little weird. But we consider values more than 2 standard errors or 2 standard deviations away to be extreme. We consider values more than 2 standard errors away from 0.10 to be extreme. But now, since 0.127, or really we might talk about percentages because the initial question was in terms of 10%, okay? Should the engineer be surprised by the observed rate of defects? No, right? Because it's within 2 standard errors of 10%. Right? So since 12.7% is 1.179 standard errors from 10%. This, I have which in my notes, which doesn't really make sense, but just go with it, which is less than plus minus 2 standard errors, right? We can go down or up 2 standard errors and it would look the same, right? So which is less than, I'm going to say plus minus 2 standard errors. So it is not considered extreme. Okay. So that's one of the tools that we're going to use to determine if something is extreme or not. I'm using that term extreme because it's going to become part of a definition later on. And so it's kind of good to get in the habit of using that. All right. The last part, and I'll just grab it here. Suppose the true population value is found to be 10%. What does this mean? This means that we're being told that P equals 0.1, right? The population proportion. If we use this proportion to recompute the value, so the standard error, I guess it's here, but instead of P hat, remember we were supposed to have P, but we don't have it. So then we replaced it with P hat and we've been told it's fine, but let's just have a look and see what the change would be, right? And so here, let's do them side by side using P hat and using P, and maybe I'll even say P hat equal to 0.127 or P equal to 0.10. Relatively close, right? We're expecting our sample proportion to be hanging out around 0.1. We just established that it's not extremely far away from 0.1, so there's no concern there. So now, how does using the P hat as our estimate, right, for P, how does that change our standard error? Spoiler alert, not that much. So the standard error of P hat is the square root of p hat q hat over n, which we found was roughly 0.0229. What if we use the standard error of p hat is the square root of pq over n? This one we'll have to calculate 0.1 times 0.9. Isn't it nice when the math comes easy? N is still 212. And this is approximately equal to 0.0206040845.9. So roughly 0.0206, right? I'd say the difference between 0.0206 and 0.0229, right? They're still in the same magnitude, 0.02, right? And so we're pretty safe to be using these, right? Our answers would change just slightly, but not significantly or drastically is what I'll say. So here, using p equal to 0.1 instead of p hat, which was 0.127, does not change the standard error drastically, right? There's still 0.02, 0.02, and then a little bit of extra. Right? Does not change the standard error drastically. Just from the hallway, it sounds like there's a storm coming. Everyone's all agitated. Thursday. I don't know. That's my prediction. There's a storm coming. But I should have checked the weather first. But that's what it feels like. Was stomping around in the hallway. All right. So that's the end of the example that we started last day. What was the point of this example? It was to show us that, okay, we understand that if I have a sample, so a point estimate, right? So a sample statistic like p hat, I could go out and I could collect a different sample and my p hat would change slightly. But then we also established that, okay, the variability is going to follow a normal distribution, which we can use, right? We can use it to calculate z-scores. I can find probabilities because of the areas under the curve, right? And so in terms of, that's the end of this example, but for a tiny bit of review, we said that p hat follows a normal distribution, which is centered on p technically, with a standard error of pq over n. But because we don't have p, we replace it with our best guess, which is p hat. But since we don't know p, we replace it with p hat. Which means that it becomes p hat follows a normal distribution centered on p hat with a spread of p hat q hat over n. Because the page ends here, I'll call that the end of our review, but let's continue from here, right? And now we can draw this curve, right? If it follows a normal distribution, I know what that looks like. And so here, pretty nice normal distribution. I guess it's Halloween soon, so we can do a paranormal distribution. It's not Halloween yet. There. No paranormal distributions. All right, so it follows a normal distribution, so we know the shape. It's going to be centered on p hat. And the spread, which we now call the standard error of p hat, is going to be the square root of p hat q hat over n. So now what we're going to do is we're going to use this distribution and we're going to use it to develop something called confidence intervals, which is one of the parts of inference that we're going to talk about. And then tomorrow we'll do hypothesis testing, which also uses this curve and all the things that we already learned. But first we need to lay some groundwork. All right, let me just scoot this down. And I'm just going to add, this is section 5.2, which is on confidence intervals. So confidence intervals, we use them because reporting just a single value, so reporting, here's my sample proportion, isn't that useful, right? That's my best guess at what P might be, right? But we're probably going to be tempted to say, okay, my best guess for P is somewhere in this range, right? Given interval. And so that's what we're going to be building up, is these confidence intervals. And the textbook uses this kind of cute analogy of fishing. So you're fishing, you can't see the fish because it's all murky. And the point estimate would be the equivalent of just fishing with a spear, right? You're just stabbing in there. You're probably close to the fish, right? But you don't know, right? And so the likelihood of actually catching a fish is very, very small, right? Which we understand. We know our sample proportion is not going to be the same as the population proportion, but we expect it to be close, right? Hence the spear. And then the confidence interval is more of a net, right? And so now we're throwing out this net and we're going to be some percentage confident that we've captured this population proportion or this fish, right? And so, all right. So instead of reporting just a single value, right, we're going to be reporting a range of plausible values for what P might be. So beside here, I'm going to say, instead of reporting a single value, right, which would be the point estimate, we're going to take the spread of the point estimate into account, right? Because I've just established that I can find the spread, right? The standard error of this point estimate. And then I can give this interval of plausible values. So instead of reporting a single value, which is the point estimate, oops, we take the spread of the point estimate which is the standard error, into account. and build an interval of plausible values. And build an interval, oops, of plausible values. Oh, for P, I should say, right? It's going to be really important that we're trying to learn about P. So all our conclusions are going to be about P, which is a little bit backwards because we'll never know what it is, right? But we're trying to communicate what it could be, right? So that's why we want to build this interval. So in terms of confidence intervals, the most kind of our default confidence level is going to be 95%. What does that look like? Well, it means that from P hat, so from our sample proportion, we're going to capture the central 95% of this distribution of P hats, okay, which is going to give me some lower value for P hat and some upper value of P hat, right? So I'm going to get this range covering the central 95%. I guess I should maybe, oh, there. So 95% is going to be our default. We will be able to do other confidence levels, but we need to start somewhere. Okay. So if I know the center and I know the spread, right? And I need to capture the central 95%. So that means that the area under the curve here is going to be 0.95. This sounds like we're heading back into the Z table, and we are, sort of. I'm going to give you a cheater way of doing it. We could just memorize them, but let's just do it properly by hand one time so you kind of make the connection between things that we've already been doing and what we're doing now. Okay. So in terms of our normal distribution, if we're talking about Z scores, right, which is our Z table. Oh, that's not very nice, but Z is centered on 0. So mean of 0. And what I want to do is I want to figure out, if I have the central 95% here, how many standard errors do I need to move away in either direction? Right? It's going to be symmetric, so we'll leverage that. But standard errors, the number of standard errors makes me think of Z, right? So that's why I'm going to convert it to a Z. And so here, I'm going to have some negative Z and some positive Z. Let's just emphasize that. I'm forcing this area to be 0.95, which means if it's the central 0.95, then I have 5% left over, or 0.05, which I have to split evenly. So that means that I have 0.025 area here and 0.025 area here. Remembering that the Z table only gives us the area to the left, and same with R, it'll only give you the area to the left. So if I want to find these values, this value has an area to the left of 0.025. Okay. If I have to find it for this one, then that's going to be this area, which is 0.025 plus 0.95, which is 0.975. But let's start with this first one here. Okay. All right. I want to find the Z score, which means that I need to find the table entry right? The table entries are those probabilities. So I need to find the table entry closest to 0.025. So here, just kind of talking about this, we need to find the table entry closest to 0.025. Whoa. Clean this up, because of course I already did it this morning. You want to be really careful that you're looking for 0.025. There are a little kind of, not decoys, but if you're not looking carefully, right, you might go for this one, 0.0025. That's not the one you want, right? So if you're in a hurry, then you want to slow down here and be really careful. 0.025 looks like, here it is, and so nice and clean too. It's almost like it's a common thing to look for. So now, right, the Z score that corresponds to this is going to be negative 1.96. Okay. Oh. Z equals negative 1.96. Yeah. Which means that this cutoff is going to be 1.96 standard errors down from p hat, right? Because I can translate it up here. Yeah. So let's see here. Let's do the same thing. Do we actually need to do this one? No, right? But we'll do it to confirm. Why don't I need to do this upper side? Because of symmetry, right? It should be the same value, but positive. But let's just confirm it. We decided the area to the left is 0.975. And I do cheat a little bit because I go and find 0.9 there. 0.975, and it does indeed track back to 1.96, which you can get there by symmetry or however you'd like. Okay. So here, this becomes 1.96, positive 1.96. Okay, so let's just summarize here. This means what? That we've captured the central 95% of the distribution of p hats by moving out 1.96 standard errors from the point estimate, right? And kind of out or away from means in both directions. So this means we have captured the central 95% of the curve if we move 1.96 standard errors away, and away means down and up, right? So just away. From the point estimate, p hat. Oh, it's like a p tilde. Can I summarize this with a formula? Why, yes, I can, right? So if I'm going away from p hat, let's start there, then I'm going to go plus minus, right? Down a little, up a little. And I'm going to go 1.96 times the standard error of p hat. Little reminder on interval notation, right? Because this is going to give me a lower bound and an upper bound. Interval notation, we use round brackets, the lower value, comma, the upper value. So this becomes p hat minus 1.96 times the standard error of p hat, comma, p hat plus 1.96 times the standard error of p hat. It's really important that you do the minus part first and then the plus part, right? Because although there is an interval from 1 to 3, for example, there is no interval from 3 to 1. It doesn't exist. All right. So kind of picky of me, but it's the truth. Right. So here, this is what we call interval notation. And we need to be aware of it, mostly because, well, if you're reporting your results, you should know how to report them. But also a lot of these questions will give you an interval, right? So you need to know how to read it. And in general, it's going to be round bracket, lower comma, upper round bracket. What if we wanted to be more general than a 95% confidence interval all the time? What would we have to change? This 1.96, right? We would have to change it to whatever z-score gives me the confidence level that I want, right? And so what we can do instead is we can call this 1.96 the critical value. That is what we call it in general. And let me just see one thing here. Okay, fine. You know what? I am going to steal it from the textbook. I did it later last class, but I think now's a good time, a better time. All right. So here, in general, a confidence interval looks like this. So if a point estimate closely follows a normal model, which later on we're going to move away from, but that's for numerical data, so we've got some time still. Okay. With a standard error of whatever SE, then a confidence interval for the population parameter is the point estimate. Notice how generic it is, right? Because we're going to be talking about different point estimates and the different standard errors of those point estimates. So this is really just kind of a template that we'll be able to use. So for each type of question now, I'm going to tell you, okay, here's the point estimate, here's the standard error of that point estimate, and now voila, you can make a confidence interval because you take the point estimate plus minus Z star, which they don't call it that, but it is called the critical, and times the standard error. So Z star corresponds to the confidence level that we selected, and Z star is called the critical value. Okay, this is where I introduce you to the cheater way. It is another table. Everyone loves tables. You guys are so spaced out. If you get one with writing on it, let me know. I can get you a freshie. These ones are yours to keep.
Does this also come with the barcode?
Yes. In fact, you already know it.
Oh, do I?
Yeah.
Sweet.
Because it'll just use the, is it P norm? That gives you the area to the left.
Yes.
Mm-hmm. And is it Q norm? That gives you the Z value? Yeah. Can't remember off the top of my head, but usually I rely on typing stuff into R and then letting it autocomplete for me. I'm like, yeah, that's the one I wanted. All right, so yes, you already know how to do it, don't worry. All right, so the table that I just handed out looks like this. Okay. And I know because I know Natalia was here, but I think it's posted on Moodle. I think I just posted all the tables. But for now, let's just kind of dissect this thing. So we went through all the work and we found that, okay, if I want a 95% confidence interval, then I need to use 1.96, right? Because then I know that the central 95% of this curve are within 1.96 standard errors. Now we're going to ignore most of this table. It's called the T table for now. So a lot of this is ignorable. We're going to use it once we get into numerical data. But for now, let's just focus on these values here. And the only thing that we're interested in are, well, this looks promising, the confidence levels. Okay. Let's 95%, it's all gibberish, but then I see a Z star, that looks pretty good. That's got to be a critical value, right? And so for now, we're just looking at this row and this row. Everything else, we're going to ignore temporarily. We will use the entire table, okay, but for now, it's pretty good. All right, so looking at this, well, let's just kind of get jiggy with it. We made a 95% confidence interval and voila, 1.96. So you don't have to do it by hand like we did. In fact, on a test, I'm going to only ask you these values, right? 90, 95, 96, 98, 99, right? It's going to be one of these. Okay. On an assignment, though, I might get you to do a 97% confidence interval, right? Something that's not on the table, then you need to know how to get there. Okay. But for now, right, 95% confidence interval. Whee. So we can use the T table to find these critical values. Use the T table to find critical values. I'm gonna move that because writing on the, wait. Oh, now I've done it, haven't I? Oh boy. Okay, well, I guess I can't move it because I've really flubbed it. Okay, I'll rewrite it. To find critical values. Right. There's nothing wrong with doing it how we were doing it, right? But it might be nice to have a little bit of a shortcut. Okay. So, all right. I won't, but I could throw you in the deep end and just give you each type of problem and give you the point estimate and give you the standard error. And then you could build confidence intervals. That doesn't really make sense, right? But just kind of knowing this setup is always going to be the same, right? That's going to be really helpful. Right? For us, we're only talking about one sample proportion, right? And so our point estimate so far has only been p hat, right? And the standard error of p hat is the square root of p hat q hat over n, right? And we know how to find z star. So before we can actually build an interval, which is just fun, right? Let's just math, plug and chug. I used to have math parties when I was in school. It was just math people who would come to my parties, so I call them math parties. And I should have had one called plug and chug, because we use that term a lot, where we just plug in numbers and you just chug away at it. You're welcome to steal my party theme, but I will want pictures. We used to have derivative offs, where you take a calculus textbook and someone just flips open and picks a derivative, and then there's a race. Yeah. Anyways, pretty fun, but pretty nerdy stuff, I guess, saying it out loud. We had fun. We need to be able to, I guess I haven't said it. We have to be able to interpret these intervals, right? If you just hand your boss an interval, they're gonna tell you it's not my job to interpret this thing, right? Anyone can build an interval, right? Anyone can do these calculations, but your job is to interpret this interval, right? So everyone thinks they're done after they've calculated, but most of your marks are gonna come from the interpretation, right? I know, right? Just want, I can see it now. I just want to plug and chug. The more I say it, it's getting weirder and weirder. But anyways, right. So the interpretation is going to be the big part of these problems. Right? Now the problem is there are a lot of ways to misinterpret this confidence interval. So what I'm going to do is I'm going to give you this kind of canned statement that you're always going to use. Okay, so if you're ever unsure of how to interpret something, you're just going to use this sentence. And I'm telling you, it's what I want you to do. It feels like plagiarism, but you have my permission. I'm telling you, I want you to use it. Okay, because if you try to go off script in the beginning, it's very likely that you're going to say something that's wrong. Okay. And I don't want you to do that. I'm trying to train your brain until eventually you're going to try to kind of get artsy with it. Stats is like the artsiest math, right? And then hopefully your brain will go, okay, yeah, I could say that because it's basically the same thing that Emily told me, right? Or maybe, no, I can't say that because, and then can kind of start there. But that's kind of how I approach a lot of these things, is I get you to memorize something, and then the more you use it, eventually it will click, okay? So hopefully that's okay. So we need to be able to interpret each confidence interval. Interval we build. And especially in the beginning, and it's totally fine if you just keep using it for life. There's nothing wrong with it. Okay, it's foolproof. I want you to use the following format. Wait, what?
Just start copying by and I already wrote down the sheet.
That happens. It's because I told you just to go with it.
Yeah.
Yeah,
But that's, all right,
let's do it. Yeah, very important. And this is going to be where, right, in the assignments and or especially in the quiz and the final exam or quizzes, right, there's going to be a spot where you enter your confidence interval and then a text box where you enter your interpretation, and then I mark that, right? And so as long as you follow through, even if your values are wrong, right, as long as you're interpreting those values, I'm totally fine with that, right? Typos happen, but the interpretation should be flawless. So we are, I always say we are 95%, so some percent confident. You could say I am, of course, but for some reason I just think I was trained to use we are. The royal we. So here, some percent confident. And this is where we insert the confidence level. 95% confident, 90% confident. And this part, people tend to not have a problem with. So we are some percent confident that the interval from blank to blank, which is of course our lower bound to our upper bound, this is where you want to make sure that you go from your lower bound to your upper bound, because again, from the upper bound to the lower bound, it doesn't exist, right? So you don't want to be confusing your client. Right? Your client being me in this case. But I don't pay very well. Okay, so far so good. We can handle this. And then now for the artsy part, captures. Okay, and that's a really important term that we use. If we say captures, really what we're saying, there's this understanding that we don't know what the population proportion is, but we're 95% that it's captured in this interval. Okay. So captures the true parameter, or the true blank, which you're going to steal from the question, but it's going to be the parameter that you're interested in. Okay. And maybe I'll say question specific. Question specific parameter. Yeah. So when I use things like true or all, right, that's telling me that this is for the population, right? And so in our case, right, once we build an interval, then we're going to be some percentage confident that this interval from blank to blank captures the true population proportion, right? For one sample proportion questions, which is what we're talking about here, right? It's going to be the population proportion. that's going to change, right, depending on what type of question I have, but it's often very safe to just take the question and reword it as an answer. Just take what did they want me to find a confidence interval of and insert it at the end. Okay. Got an example, but before I do, this idea of only being 95% confident, right? That's because if I go through and I do repeated sampling, right? So if I generate many confidence intervals, only 95% of those would capture the true proportion. Now, I forgot to mention the margin of error, I think, but there's still time. Just remind me. Where is it? Where is it? Where is it? I think I got too excited. Oh yeah, here. So this is really just to illustrate what would happen. And I'll just keep it kind of small here and zoom in instead. Because it's just to illustrate, right? You don't have to copy this down, but figure 5.6 from the textbook. Of course, there. Okay. What they've done is they've taken that scenario where we pretend to know the population proportion, right? So we generate a population, so we simulate this population. And then what they did was they took 25 random samples, right? And each of these dots represents the sample proportion, right? And as we already said, right, they're going to move around, right, constantly hovering around the population proportion, which we don't ever know, but in this scenario, just to illustrate, right, this is what it would look like. So each of these little dots is the p hat, and then we've built the confidence interval around those p hats. Right? And so these are all 95% confidence intervals. And the reason we're only 95% confident is because there will be scenarios, and we won't know when that is, there will be scenarios where our sample proportion is too far away from the population proportion, so our confidence interval does not capture it, right? But only 5% of the time. So only 1 out of 25 is where that happens. So that's why we can only be 95% confident that we're capturing the population proportion. In this example, we knew what it was because we made it so, right? But that's what's happening in real life as well. Now, can I be so bold as to go back? Oh man, okay. Did I do everything on this page? Yes. To this general confidence interval, I just want to highlight that this plus minus chunk, which I call it the buffer, right? Down a little, up a little. It's kind of a buffer, but it's called the margin of error. Again, it's good to know. A lot of papers, research papers, will just report the margin of error. Okay. And also a lot of the questions that you're going to do just ask you to use the margin of error. So then they've already done the work of finding Z star and multiplying it by the standard error, right? So it's good to know what it is. Okay. Good. Let's do an example. Let's see here. I'm going to do exercise 5.13. Okay. So especially in the data science side, you can see this happening. So a website is trying to increase registration for first-time visitors, exposing 1% of these visitors to a new site design. Of 752 randomly sampled visitors over a month who saw the new design, 64 registered. Okay. There's a decoy number in here, and that's the 1%. Right, so don't be thrown off. That can happen. But our sample size is going to be 752. Right? So let's just jot that down before we can do anything else. So N is 752. The 64 is the number of successes, right? So X is 64. From here, I can go ahead. I could find the sample proportion. I'm going to hold off because it's going to hold my hand through the entire procedure. Yeah. Sometimes I jump the gun though, and I just go for it. But trying to hold back. First thing we have to do is check any conditions required for constructing a confidence interval. Those are the same conditions that we established last day, right? We have to have independence, which we get by randomly sampling, right? Or we're able to assume by randomly sampling. So that's good. And then we have the success failure condition, right? At least 10 successes and at least 10 failures. So part A, we have to check the conditions. First one is independence. The visitors were randomly sampled. The visitors assigned to see the new design were randomly sampled. See the new design were randomly sampled. Yeah. Which means, right, that whether they registered or not is independent for each visitor, right? Or that's something that we're assuming. Okay. The second condition is the success failure condition. In this case, right, it is N times P hat has to be greater than or equal to 10, but I also have the number of successes, so I'm just going to go for it. So X is 64, which is greater than or equal to 10. Let's just make a note here that N times P hat is the same as N times X over N. So N over N cancels. So you can just use the number of successes, right? If you have them. Which we do in this case. Oh, and I guess H equals X. If I have 64 out of 752 are successes, then of course the remainder must be failures. So N minus X is 752 minus 64, which is 688, which is also greater than or equal to 10. Booyah. This allows us to use the normal distribution, right, to find the confidence interval. Okay. Part B, compute the standard error. The standard error of this one sample proportion which means we need to have P hat first. So let's start there. x over n. So p hat is 64 over 752. .0851, I'll round to 4 decimal places. And then I'll do it to the side here. The standard error of p hat is still the square root, let me see here. Square root of p hat q hat over n, which is the square root of 0.0851 times 1 minus 0.0851. Divided by n, which is 752. Gets me to approximately 0.0102. And this is the standard error of p hat. Okay. Got these components now. That's great. And compute the standard error. We did that. So now we're ready for C. Construct and interpret. Oh, done. A 90% confidence interval for the fraction of first-time visitors of the site who would register under the new design. And then it has a follow-up, assuming stable behaviors by new visitors over time. But let's just ignore that. That is something we're assuming, right? But we'll ignore that. Okay. So we want to make a 90% confidence interval for the fraction. Now a fraction is a proportion, right? Just another decoy. For the proportion of first-time visitors of the site who would register under the new design, right? We're going to parking lot that and use it in our interpretation, right? That blurb. But for now, let's plug and chug and find the 90% confidence interval. So remembering that the confidence interval for one sample proportion, okay, and without having seen other types of questions, it's hard to illustrate why this is a one sample proportion without sounding kind of condescending, I guess, because we have one sample and we have a proportion from that one sample, but later on we'll have others in the mix, and so it'll be harder, honestly. But okay, p hat plus minus the z star for a 90% confidence interval times the standard error of p hat. We need to find, right? Because I have p hat, I have the standard error of p hat. So the only thing that I don't have yet is the z star. So we need to find the critical value for a 90%. I'll say CI, confidential informant, no. Confidence interval, I'm gonna use that abbreviation a lot, get used to it. How are we gonna do that? Well, I should have, and I feel like I have in the past, where I have just this chunk of table ready to go. But I don't remember where I put it. Isn't that a pickle? Keep it on the same page here. I will put it back on. Come on, work with me. On the same page here. There. Okay, so again, looking at these confidence levels and only the Z stars for now. And we want a 90% confidence interval, so our Z star is going to be 1.645, which means that we're going to go 1.645 standard errors away from the sample proportion. Like I said, the math is not hard. It's the interpretation. I'll just jot down the formula again here. P hat times plus minus Z star times the standard error of P hat. P hat we said was 0.0851 plus minus, and we just found that it's 1.645 times 0.0102. Remembering that this kind of buffer portion is the margin of error, so let's calculate the margin of error, because that might be nice to have. I get 0.016779. And let's just remember that this is your margin of error. There are instances where questions will just give you the point estimate and the margin of error. So then you would just skip straight to here. Once I do this calculation, I get an interval. Remembering, even though it is plus minus, of course, you have to start with the minus part to get the lower part of the interval and then do the addition. And we get 0.068321 up to 0.101879. All right, remembering that it's really important that it's lower than the upper. I feel like I've said that 10 times, and usually I say it way more, and I still see the intervals in the wrong order. Just remember, it doesn't exist. So we can talk about it in terms of proportions, or if we want to talk about it in terms of percentages, we can, right? 6.8% and 10.2%. Right. So, or as percentages, which is how we usually report proportions. 6.8% up to 10.2%. Oh, and maybe I'll just do the rounded proportions. Is between 0.068 up to 0.102, rounded to 3 decimal places. Okay. Now we're ready to interpret this interval. Interpret the interval. So I'm going to steal that kind of blank, fill in the blank one that we just wrote out. And I'll empty it. Okay. Here we go. We built a 90% confidence interval, so we are 90% confident that the interval from, and here it's dealer's choice. I think the question was asking, and let's remind ourselves what the question was specifically. Question was in terms of the proportion, copy. Let's see here, the fraction is the proportion. But I think most people would understand if, oh, come on. Proportion. If you reported it as a percentage, of course, if you're doing it in an assignment, right, it'll be specific. Okay. But we're 90% confident that the interval from, and if we're going to do the proportion part first, but then I also want to show you that we could report it as the percentages. Gets confusing, right? Because we've got some percent confident, and then we've got percentages, but the context will tell you what's going on, right? And so the interval from 0.068 to 0.102 captures the true, and this is where we steal from the question, the true proportion or fraction of first-time visitors of the site who would register under the new design. But it feels really good, right? You're just kind of rewording the question as an answer, so you get to write a lot, but not think a lot. If that's a nice thing. Really goes to show what my values are. All right. Okay. We could also do it with the percentage, right? But then you would say for the captures the true percentage of first-time visitors of the site. So depending on what it is you're reporting. Captures the true. Here we have the proportion, but if you reported the 6.8% and the 10.2%, then you would change this to percent or percentage.
Percentage
of first-time visitors of the site who would register under the new design. Riddle me this. Wouldn't it be more interesting to know what the difference was between the old design and the new design? Sounds like 2 sample proportions to me, which we will be able to do, right? But for now, I know I'm out of time, and we did it. Good job. Yay! If you have any questions, let me know. Otherwise, I will see you tomorrow. Bye, Natalia.